This is Physics 241 lab. Today's lab's lab 12, covering the buoyancy of water. In this lab we're not going to use the computer at all, but we will use the vernier interface and a force sensor to measure the force. As you know, water has a buoyancy force, and it also has a density, which we refer to as rho. The density of water is about 1,000 kilograms per cubic meter. And in this lab, we're going to prove that. And what we start with is Newton's second law, F equals ma. We manipulate some of the variables to introduce density into the picture. And then we isolate variables, and we see that the density is the change of the force in newtons divided by the cross-sectional area in square meters times the height of the object in meters times gravity, 9.8 meters per second squared. Now in today's lab, what we have is we have an elevated force sensor. The force sensor has a weight hanging on it, and the weight is hanging over a 1,000 milliliter beaker of water. The water is filled to about 700 milliliters. And what we're going to do, the force sensor is hooked up to our vernier, which will be measuring force. And initially, the force sensor is just measuring the downward force of the weight. What we have here is a jack lift, and we're going to push the container up into the water. Into the weight. And what the water will do when the water rests on the weight, the buoyancy of the water will relieve some of the force pressure from the downward motion of the weight. And that'll be reflected on the force sensor. And we're going to have two conditions. We're going to have the weight halfway submerged into the water, and we're going to have the weight fully submerged into the water. The amount of water that the weight displaces will be a function of how much of the force the buoyancy is going to take up. Now what we have is we have cylindrical weights, weights that are cylinder-like, and we're going to do 4 trials with these cylindrical weights. We're going to weigh each one, and we're going to measure the dimensions of each one. And the 4 weights we have are 1,000 grams, 500 grams, 200 grams, and 100 grams. And we've measured the diameter of each one of these cylindrical weights and the height of each one of these cylindrical weights. And it's listed here. And because we're going to submerge the weight halfway down, we also have a dimension of half of the height. And then knowing the diameter, we can come up with the cross-sectional area of each one of these weights. So what we do is we submerge each one of these 4 weights into the water, and we take a force measurement. We take a force measurement halfway down, and we take a force measurement when the weight is fully submerged. Before we do that, though, we check the calibration of our vernier. We know these are our weights, and we know the force, the calculated force, is simply each one of these weights times gravity. And then before we submerge the weight, we take a force reading on the vernier and we compare it to our calculated force, and we can see that the calibration is very good. Our final step, though, is the actual submergence of the weight. Again, this is the kilograms in the 4 instances. This is the diameter of the weight, the area of the weight, the height of the weight. So what we did in our first scenario is we submerged this 1 kilogram weight halfway down into the water, and we found the change in force was 0.76 newtons. Then we fully submerged it and got 1.62 newtons. And we did the same thing with half a kilogram, 2/10 of a kilogram, and 1/10 of a kilogram. And we got delta F readings. And as we said earlier, our calculated density is a function of the change in force the area, the height, times 9.8. We have the height here, or the half a height, depending on whether it's fully submerged or partially submerged, and the cross-sectional area. Plugging all these things in, we calculated our rho. And we got somewhere between a high of 934 and a low of 443, and our average was 801 kilograms per cubic meter. The actual density of water is 1,000 kilograms per cubic meter, so we're running about a 20% error. But anyhow, the whole purpose of the lab is to show that water has some buoyancy, and as a weight is submerged into the water is pushing back up against that weight. That's what the change in force is. And knowing that factor, we can calculate the density of water.